So starting with problem number 1. So we need to find the Thevenin equivalent for this circuit, and also we need to find the voltage VL, the load voltage, at different values of the resistor. So here, first of all, we can see that on our circuit there is only independent sources, so we can just find V Thevenin just straightforward. So we remove this resistor, then we find open circuit voltage at this point. So between this and this, it's actually because there is no current here, it will be the voltage drop across the 3 ohms. So V Thevenin will equal 9 over 2 plus 3 times 3 will equal 5.4 volts. For our Thevenin, we just kill all the sources, so we will get 2 ohm and 3 ohm and also 1 ohm. So 2, 3, and 1. So this is R Thevenin. So R Thevenin will equal 2 in parallel with the 3 plus 1. 2 in parallel with 3 ohm plus 1, so it will equal 2.2 ohm. So now our equivalent circuit will be, this is V Thevenin, that's equal 5.4 volt, and R Thevenin 2.2 ohm, and this is our load RL. This is our load RL. Now we just need to find the voltage with different values of the resistor. So the first value is VL will equal 5.4 over RL plus R Thevenin. RL plus R Thevenin, this is RL. It will equal 3.2. This will equal, of course, times 1, the resistor. It will equal 1.6875 volt. VL, in the second case, 5.4 over 5. This is VL, this RL plus R Thevenin times 3.5, so will equal 3.316 volt. Last case, sorry, before the last one, 5.4 plus 22.2, 6.257 times 6.257, so it's equal 3.995 volt. The last one, VL, 5.4 over 2.2 plus 9.8 times 9.8 will equal 4.41 volt. So we solve this one. We move to the second one. The second one, we need to find R equivalent. It's the same circuit, by the way. It's the same circuit here, but here we need to find the power in the range from 0 to 5 ohm. So we have already found the equivalent, R Thevenin equivalent for this circuit, so we just use it to find the power. So these circuits can be represented by just 5.4 volt. Yeah, sorry, 4.5 volt. Yeah, 5.4 volt. 5.4 volt in series with 2.2 ohm. Then this is the load. This is our load. By the way, we can find the short circuit equivalent or I Norton for this circuit. If we replace this with a short circuit, so I short circuit will equal 5.4 over 2.2. So I short circuit will equal 5.4 over 2.2, which is equal 2.455 amp. This is I Norton. Now we will find the power in the range from 0 to 5. So here, or for the different values of, so here RL is 1, 2.2, 2.2, then 3.5, then 6.257, then 9.8. And here we will have VL and IL, and here the power. So in each one of them we have already found VL 0.68, 7, 2.7, 3.316, 3.995, then 4.41. So just a voltage divider. For calculating the current, it's easy for us to use Norton equivalent. So we convert this to a resistor and a current source. So this current source is equal 4.5 amp in parallel with 1.2 ohm. So this is my RL. So I can use just directly the current divider here. So IL will equal 1.406, 1.023. Then please check all the numbers, 0.79, 0.532, and 0.375. So the power just be the multiplication of the current and voltage. So 2.373, 2.7621, 2.62, 2.125, and 1.654. So we're done with problem number 2. So we go to number 3. In this problem, we need to find the Norton equivalent of this network and also Thevenin equivalent, and we need to find the current for different values of resistance. So here we use this circuit. So here it's how to find Thevenin Norton equivalent. We replace this one with a short circuit. So when we do this, we will end up with 1 amp current source. Remember that I have here 0.8 ohm. This one is 0.8 ohm. 5 ohm and 5 ohm, they can combine together to become 2.5. Now, when this becomes a short circuit, what happens? The 2 ohm also becomes short circuit. So the current will only flow into the short circuit. So this will be my I Norton. I Norton will equal 1 amp. We just apply a current divider times 0.8 over 2.5 plus 0.8, which is equal 0.242 amp. For our Thevenin, it will be, when we replace this with open circuit, so 0.8 plus 2.5 all together in parallel with 2. So our Thevenin, or R Norton, yes, the same thing. So in parallel with 2. So this 2.5 plus 0.8 becomes a 3.3, so in parallel 2, so R Norton will equal 0.24 ohm. Now we can also find the open circuit or Thevenin equivalent. So Thevenin equivalent will equal 1. You can see this becomes open circuit, so 1 times 0.8, yeah, over 0.8 plus 2.5 plus 2. This is the current here. So then we multiply the current in this resistor. Then we multiply by 2. So this is our Thevenin. Now we can find the RL for each value of the resistor, for each value of the resistor. So IL will equal Thevenin over the total resistor. The total resistor, this is Thevenin resistor plus the load. So the first one becomes 0.135. When it's short circuit becomes when it's not short circuit, because when it's 1, yeah, when it's 1, then at 4.92, so 1.245 plus 4.923, this will equal 0.049 amp. The last one, the same, we just do the same. So here you find that RL and IL. So 0, this becomes 0.2421, it becomes 0.1354, 0.923, it becomes 0.049. When it's 0.807, it's 0.0323. Okay, we move to problem number 4. So here we need to find Thevenin equivalent for these circuits, and also we need to find the power dissipated in a 100 ohm resistor. It's connected to the terminal of this circuit, and also we need to analyze the circuit, the original circuit without Thevenin equivalent. So first of all, we will find our Thevenin and the open circuit for this circuit. So we need to do the analysis. So first of all, in order to find the open circuit, we need to find the voltage here. So we know that there is no current here. So we can just apply mesh analysis. It's easy for us to say this is 1 and this is 2. So here I will apply mesh equation for the first mesh, starting from here. Minus 0.7 plus 45 I1 plus 120 I1 minus I2 equals 0. This is my first equation. My second equation, I2 equal minus 0.3. I think it's easy for us to solve them to get I. We can just substitute I2 into the first equation. Then we will find that I1 equal minus 0.15 amp. From this, we can find the V open circuit. So V open circuit will equal the current in this resistor plus the current times this resistor plus 0.7. So we can just apply KVL around this loop. So the open circuit will equal 0.3 times 0.75, yes, 0.375 plus 0.7 minus 0.215 times 45. This is I1. Okay, then the open circuit voltage will equal 3874 volt. R Thevenin is clear when this is short circuit, so 45 in parallel with 122, then in series with 75 and 22 because this becomes open circuit. So R Thevenin will equal 120 plus 75 plus 220, so will equal 370.87 ohm. Or we can say that I Norton equal, we divide the voltage over the resistor, becomes 100.3 milliamps. So our equivalent circuit here, becomes here Thevenin equivalent 3.32.87 volt and 328 approximately, yes. Then this is the 100 ohm. So it's easy for us to find that the power will equal the voltage over the total resistor. 100 plus 300, yes, becomes 208. This is the current. The current squares time the resistor will give us the power. So the power becomes 590 milliwatt. So for the second one, you can just, for the other way of solution, you can just replace this open circuit with a 100 ohm and then try to find the power in this resistor using the conventional methods. We move to question number 5. In question number 5, we need to find Thevenin equivalent between these two terminals. We need to find Thevenin equivalent between these two terminals. First of all, of course, we don't have any dependent or independent sources. So our Thevenin calculation, I think, is straightforward. So our Thevenin, just this resistor, these two become in parallel, then become in series with 2, then become in parallel with 5. So we can say our Thevenin, because 3 and 1, this becomes together, so they become 3/4. So our Thevenin will equal this 3/4 plus 2 plus this 2, then they become in parallel with the 5 ohm. So this becomes 1.774 ohm. Now for V open circuit, it's easy for us to apply nodal analysis. Yeah, we can apply nodal analysis. I will recall this 1 and 2. So my V Thevenin will be just V1 minus V2. Then I will write my KCL equation. So I write KCL here at node 1. So V1 minus 2, remember, minus because we have a minus 2 over 2. This current is leaving. The current in this is V1 minus V2 over 5. The current entering is equal to, so this is my first equation. My second equation is V1 over 1. V1 over 1 plus V2, this is V2 over 1, plus V2 minus V1 over 5, and plus this current is V2 minus 4 over 3. There is no current entering this node, so it's equal 0. So we have two equations. After we solve them, then V1 becomes 1.7419 volt and V2 equal 1.0968 volt. So V Thevenin will be just the difference between them. So V Thevenin becomes 0.645 volt. So this is our V Thevenin, 0.645 volt. Our Thevenin is 1.774 ohm. So we have done with question number 5. We go to question number 6. For question number 6, we have a circuit that we need to find the equivalent of it. So here we need to find Thevenin equivalent for this circuit. Now, please note that this circuit has only dependent source. So what we need to do now, we need to assume a test current. We will assume a test current because the circuit does not contain any active element. So here, this is becomes our, this is the 10 Vx. Then this is the 21 ohm resistor. And what I will do here, I will assume a test current equal 1 amp. Then I will find the voltage here. Remember, this can be replaced only with a resistor, on the resistor. So R Thevenin will equal this voltage over 1 amp. Or we can see this V, or remember this, or I will call this just Vx. Yeah. So, but remember this will be in ohm. So I can write here nodal equation. The current here is equal to Vx over 22. The current here entering is 10 Vx. So 10 Vx plus 1 amp. 10 and 1 amp are entering. They equal the leaving current, which is equal Vx over 21. When we solve this one, becomes Vx minus 0.1005. But remember, the resistor, we do not replace it with a positive negative sign, so it's better to write it 0.005. Oh. We move to question number 7. In question number 7, we need to find a Thevenin equivalent for this circuit. But what you notice here, we have both dependent sources and independent sources. So what we do when we have this circuit, we find Thevenin equivalent by first finding the open circuit voltage, then we find then the short circuit current. Okay, so our circuit here, it's the best way to solve this problem to use mesh analysis. So I will assume this is 1 and I will assume this is 2. So I will write 2 equations. So here for this one, it becomes 500 I1 plus 2 Ix, this source. Then I cannot go to this source, so we form a super mesh between 1 and 2. So then 1.5 K I1 minus I2. 1.5 K I1 minus I2. 1.5 K I1 minus I2 plus, sorry, this one, no, this 1.5 K, this one only I2. So here 0.5 I1, 500 I1, then 2 Ix, then 1.5 K I2, 1.5 I2. Then plus 2.5 K I2 equal 0. Here we have Ix. Yes, you can see that Ix equal minus I1. Ix will equal minus I1. So we substitute this one. So when we substitute this one, you will find that this becomes 498 I1, and what we have here, then this becomes I2, so 1.5k plus 1.5k and 2.5k, so they becomes 4k I2 equals 0. So this is first equation. Second equation that we have I2 minus, sorry, we say that better I1 because I1 is doing it. So I1 minus I2 equal 0.7. I1 minus I2 equal 0.7. So this is my first question. Why? Because I1 is in direction of the current source. So after we solve these two, we will find I1 and I2. So we are interested in I2. I2 will equal 0.0775 amp. Now, as you can see, the open circuit voltage is just the voltage across this resistor. So V open circuit will equal 1.5k times I2. So it equal 116.25 volt. Okay, so here we determined V Thevenin. The second stage we need to find I Norton or the short circuit current. For the short circuit current, we just redraw the same circuit here. We have 500. We have plus minus 2ix. We have 0.7 amp. But what we have here, when this is short circuit, so the 1.5 kilo ohm will not be in our circuit. So I will redraw this. This becomes I short circuit, and this is 2.5k, the same. So I will call them I1 and I2. So my short circuit current will be just I2. Do the same analysis here, and you will have two questions. You solve I1 and I2. You will get that I1 will be equal 0.5837 amp. I2 is your short circuit current that you want to calculate. It will equal minus 0.163 amp. So you determined I short circuit and you determined V Thevenin. So from these two currents you can find R Thevenin, the equivalent resistance for this circuit. So R Thevenin will equal V Thevenin over R Norton, so 0.1163, so it's equal 1 kilo ohm. Okay, we go to the last problem in Thevenin. Here we need to find the power dissipated in a resistor connected to the two terminal, if it's 1 kilo ohm or 4.7 and 10.5 for kilo ohm. So in this case, of course, we need to replace all the circuit with a Thevenin equivalent. It becomes easier for us. But here we have both independent and dependent, so the same. We apply the open circuit voltage and the short circuit current in order to find the current. So for the open circuit, I think we should determine two currents, 1 and 2. This is 1 and this is 2. Then we can just write KPL equation. So starting from here, 10k I1 plus 1 volt plus 20k times I1 minus I2 equals 0. Then the second equation is just straightforward. I2 equal 0.02 V1. Now we have a dependent source, yes? So we relate V1 to the current. It's clear that V1 will equal, because the current is entering from the negative, so V1 equal minus 10k times I1. So we just substitute it here. So then I2 will equal 0.02 minus 10k I1. So after we solve these two equations, we will get I1 and I2. I1 will be equal minus 2.48 10 to the power 7 amp. I2 will equal 4.962 10 times amp. Then, of course, our open circuit voltage will equal I1 times what? I1 times 10K. I1 times 10K, so it becomes minus 2.4813 millivolts. So this is the first stage. The second stage, we need to find I short circuit, because remember your circuit has independent and dependent source. Now, but what happens when I short circuit this? Please pay attention. This resistor is in parallel with the short circuit, so V1 goes to 0. When V1 goes to 0, of course, this will not be in our circuit, and also this current source will equal 0, so it becomes open circuit. So my circuit will have only this 1 volt source and the 20K. It becomes much more simpler. So it's easy for us to find I short circuit just 1 volt over 20K, because it's the current here. Yes, remember, it will be the current here. So it becomes 50 microamps. So R Thevenin from this one, R Thevenin will equal 49. Please check. It will equal 49.626 ohm. You just divide the voltage over the current. And then it's easy for you to find the voltage in each case, because now your circuit is just minus 2.4813 millivolt in series with a resistor 49.626 ohm. So here you're connecting your load. So the load power will equal, okay, I think we need to find the current before that. So the current is equal the voltage, what we have, this is the voltage, 2.481 10 times 3 over the resistor. What actually the resistors? You have the 1,000 and the 400. So 1,462. So this is your current. We square the current, then we times the RL. This is my RL. So then I will get the power 5.587 nanowatt. The same for RL equal 4.7K. The power will equal 1.28 nanowatt. Please check. And for RL equal 10K, 0.54K. So the power will be equal 578.5 picowatt. So please check all the number.